Recording in progress.
Yeah, so good afternoon, everyone. Welcome to the Radio Astronomy Techniques seminars. So those of the audience who are new to this series, I would like to introduce this. So India is a full member in the Square Kilometre Array, and we are looking forward to a lot of exciting radio astronomy in the next few years to come. And in preparation for that, we started this radio astronomy techniques seminars to share and discuss new techniques emerging in radio astronomy for imaging or data analysis in general. Today we welcome Dr. André Offringa for his talk in this series. This is the fourth talk in this series, which we started in April. So let me briefly introduce André Offringa to you all. So he completed his PhD at the Kaptein Astronomical Institute in the Netherlands, and then went on to do his postdoctoral fellowship at the Mount Stromlo Observatory, which is a research school of the Australian National Institute. After that, he's been at ASTRON, the Netherlands, for almost a decade. He's currently the head of LOFAR Science Group and also an assistant professor at the University of Groningen. He, as many of you know, is well known for his softwares, basically the WS Clean and AO Flagger, among the many that he has developed. So today, he's here to tell us about basically algorithms for radio astronomical interferometric processing. So welcome, André, and over to you.
Thank you very much, Ruta, and thanks for inviting me. I was happy to talk about this subject. If you have any questions along the way, please just raise them. I am very happy if we discuss things or explain things. It's also hard for me. I don't know many of you, so it's hard for me to estimate my audience. So if I go too quick or too slow, just tell me. So my next slide is my introduction, but I think this is mostly covered already, so I'll skip most of it, but yeah, what to say about it. I also have a horse, as you see on the right, and yeah, my science interests are epoch of reionization, and I have also done some research on the synchrotron background radiation, but my specialty is low frequency science, and within that, mostly I do a lot of focus on algorithms. So this is what I will try to cover if time permits. I'm gonna talk a little bit about WS Clean, and WS Clean you can see it as two tasks that it performs. It does gridding and it does deconvolution. I'll cover AO Flagger a little bit, radio frequency interference flagging or detection, and also cover visibility compression a little bit, and then I'll go a little bit into the general challenges that I've learned along the way with these subjects. So as a brief introduction, I think you probably are all aware, since you probably all or are familiar with the GMRT, but also LOFAR produces large data volumes. This is a graph, an already very old graph. I couldn't find a new one, but of the downloaded data of the LOFAR archive, which reaches 3 petabytes per half year, basically. And this is 6 years ago, so we became more efficient, so it's a lot more nowadays. So there's a lot of focus on processing these data in an efficient way, and that's why it's important that we continuously improve our algorithms and make them more efficient, but also get the last bit of science out of those data to get the best images. I will mostly focus on imaging, in contrast to, so say, beamforming or time measurements of sources. So really interferometric mode, that's sort of my specialty. For for you who don't know LOFAR, so this is the core of the LOFAR telescope. It has all these little antennas stacked together on an island, not so far away from where I am here in the Netherlands. And it's split up in two frequencies. These are the LBAs. They're 10 to 90 megahertz, and these are the HBAs, high band antennas, and they cover above 100 megahertz. And this is the core, and there are quite a lot of remote stations in the Netherlands, and we also have international stations, which together give us baselines of several thousand kilometers and good sensitivity. So yeah, if we talk about processing, LOFAR is challenging, because if we want to get everything out of LOFAR, we would like to image with a resolution of 0.3 arc seconds. And our full beam is 1.5 degrees at these baseline lengths. And that means basically that we have to make 100K by 100K images. So 100,000 by 100,000 pixels. So then you're talking about 10 to the 10th pixels. And that's challenging. Even one image already wouldn't really fit in a low-end laptop nowadays. And for the Square Kilometre Array, that's going to be the instrument of the future, of course. We would require similar image sizes. Now, one of the goals of LOFAR is to survey the whole sky at its highest resolution. This is very challenging because it requires basically, at the moment, more compute than that we have. But I'll show you where we are. So this is how we process data with LOFAR, sort of split up in three parts. We first have a initial stage, because the initial data is at very high resolution, say typically 1 arc second, a few kilohertz. So that's what comes in here. And that it's nice to have it at high resolution, because RFI detection works better if you have high resolution data. You lose less data, and you can find more the RFI more precisely. But immediately after that, we can do averaging to reduce the data size quite a lot. And after averaging, we also do disco compression, and I'll talk about that later. But the nice thing about this is that the output is a much reduced data set that can go into the next stages. And normally this is also the point where we archive our data, so for users. So all of this on the left is basically trusted to do by the observatory, and astronomers don't tweak this at all. There are sometimes a few more steps done here, but also what we are trying to do with our observatory is basically to push this more towards the right, that the observatory in the end actually does all of this instead of all the astronomers, because it's still quite an expertise that you need to have to do all this. So after this initial processing, which we normally call the compression pipeline, we start calibration. And in calibration, we basically, the first step is direction independent calibration, which basically means that we assume that all the sources in the sky are affected in the same way by things like the ionosphere, the instrumental response, etc. And then we get a first image out, but this image is not something that we normally use for science because it's of low quality. But it's again a nice point to hand off data to a next pipeline, because here you have a first model. You have you can often reduce your data a little bit more, and then this step normally takes about a day, 24 hours. This pipeline for an 8-hour observation with the full bandwidth. And then the next step, that's the expensive part. There we do direction-dependent calibration and direction-dependent imaging. So here we no longer assume that all the sources are affected in the same way. We calibrate for the ionosphere, and we calibrate for things like an imperfect beam model, an imperfect model for how our instrument response is to the sky, which needs to be done to get a good image out. And then only then we have an image that is sort of science quality. So yeah, the whole pipeline takes up to several days to run for a whole 8-hour observation. So that was just a bit of an overview, and then I'm slowly going into to the individual steps that are performed. And one of them is imaging, and you can do this direction independently and direction dependently, as I explained. And if you talk about imaging, you more or less assume that your data is calibrated to the best effort at that point. That's what goes in. And then there are two important steps in imaging, and one is gridding and one is deconvolution. And this is an iterative process where you go around. So gridding means when you have your visibilities, they're in continuous UVW coordinates, and gridding puts those on a regular grid. And that's an expensive operation because you need to do a convolution and you need to correct for W terms, where I will talk a little bit about. So, and you need to go through all your data, which is also important because that, basically this block means a pass through all the data. And a data set can be several tens of terabytes. And for the SK, that will even be several hundreds of terabytes, maybe even a petabyte. I don't know the sizes from the top of my head, but it will be larger. And then we get into a deconvolution block, and I'll go over what these do, but this is iterative. And the outputs of imaging are several. You get your model visibilities, which is basically a prediction of what the instrument would see given the model that we created, the sky model. Now then, what's most interesting most of the time is a restored image. This is basically just the image of the sky, the best possible image at that point. And what also comes out is a model, and this can be an image where you just see the pixels basically marked where we think there's a source. But something that WScreen also can do is it produces a list of sources, and this is often a very compact way of representing such a model, and also allows to very efficiently cover this in calibration, because such a list can it can consist of point sources, but it also can consist of little Gaussians. And an image you can't make up anymore what would be Gaussians or what would be point sources. But in that list, it's a very compact representation of that. Now, that's imaging at a very high level. Well, this is sort of where I will go through all the methods that are available, at least in WScreen. So I'll talk a lot about WScreen. It's a package that I wrote originally for the MWA, where we needed something which was faster and less memory hungry than CASA. And I kept extending it, and I would say, in my personal opinion, it's the most advanced imager that's available at this moment. Now, it has several features to do different kinds of grading. I will go over this, but there's also several deconvolution algorithms. Okay, so let's go back a little bit. Some of you might all know this, so I'm sorry if I'm repetitive, but I hope to get everyone along. So the output of an interferometer follows this function. So if V is a single visibility, it can be parameterized by coordinates. I'll go over those coordinates in a little bit, but we call those UVW. And it's an integral of this where I is an image of the sky. So you can think of it if you have a specific L and M, which you can think of as a two-dimensional image. This will be a non-zero where there's a source, but it can be zero, of course. Well, the sky is not zero anywhere, I would say, but it will be near zero where there's not a source. But then you see this term, which is a phase term, but and given with the integral, this becomes a Fourier transform. And the task of imaging is to basically estimate I from V. And because this is almost a Fourier transform, you can do an inverse Fourier transform, but you're not quite done yet. So as I was already talking about UVW, this is how those coordinates are defined. W is in the direction that your instrument is pointing, and U and V are orthogonal to that to form a three-dimensional axis, and L and M are positions on the sky. Now, and then that's how we express the baseline. Now, and because of the rotation of the Earth, we sample different values of this function. And then we get something like this, which is a UV coverage. So again, these are points where we have measured. So each of these circles is a single baseline, a single pair of antennas correlated together. And if you observe for, well, it would have been 6 hours or so, you get all these tracks through the UV plane. After gridding, you can do a Fourier transform of this, and then you get a first image. Now, I was already saying this is a Fourier transform in some way, but not quite because of this W term here. But what was originally often done is because the field of view was quite small, W was near 0. Now, and if you look at this, if W is near 0, then basically this whole term on the right falls away, and then it's a perfect Fourier transform. So that's what you get here. And then you can just do an inverse Fourier transform, or actually the inverse of this, which is the normal Fourier transform. And then you get a first image of the sky. Now, the only issue is that with low frequency instruments, and that holds for LOFAR, but it also holds for GMT, and it holds for the MUA and many other telescopes nowadays, you don't have a small field of view. Because your field of view is scales with well, your inverse frequency. So low frequency have naturally a large field of view. So the assumption that W is 0 no longer holds. And this is really where why I originally built WSClean, this imager, because there were not many packages that could deal with high W values very well, or high L and M values. So that's the field of view. Now, and once you have done all this, if you do an inverse, you get a first image like this. And yeah, if you look at this, it's not perfect yet. It's still convolved with the point spread function, and that is because the instrument, because we did a Fourier transform of something which was incompletely measured. We had this UV coverage, so you can see that as a multiplication by a sampling function, by something where what you've sampled are ones and what you've not sampled are zeros. Now, and a multiplication in Fourier space is a convolution in image space. So that's why you get something like this, which has all these rings around it, which is basically the point spread function shown at every source. Hence, we also need to do something about that, and that's called deconvolution. Now, and the most common method is Högbohm clean. I'll also go quickly over this in the risk that all of you already know it. But in 1974, Mr. Högbohm, Jan Högbohm, found this very simple algorithm where if you have an image, a convolved image, you search for the largest peak. Then basically we know what the point spread function of the instrument is because we know our sample function. We can place that point spread function on the source and subtract a little bit away from it, so that we are sort of reducing the contribution of that source. And you can do this iteratively, and if you then record where you place all your sources and restore those in the end, then you get a deconvolved image, and that's the image that we are looking for. Now, this is the most simple algorithm, but there are many more. So going forward, so I've discussed this a little bit, but now I go a little bit into the gridding algorithms first that are out there. And the one that I originally started with for WSClean was called W stacking. CASA had a method which was called W projection. So remember that it's not quite a Fourier transform, and we have to do something with this W here. And if you look at this term, you can actually see that this is again a multiplication with this term here. If you extract it from the exponent here, so there you can see this as some kind of multiplication. You could put it in front here, and then you can also sort of handle this in the inverse by doing the opposite, and that would be a convolution again. So again, the convolution theorem here. That's what W projection does. So you have a visibility, you convolve it with something which corrects for this term here, and then you can place it on the UV plane. You take a Fourier transform, and then you have your, well, at that point still dirty convolved image. But a different approach is to use a method called W stacking. Now, there is an issue with this method, and it is that if your W terms are sort of large, or your field of view is large, this convolution, the support of it becomes very large. And that means that for every visibility, you have to convolve it with a very large term, which becomes both very slow and also very memory hungry. So in W stacking, we do something differently. We take a visibility and then we divide it into different planes, which all represent a different W term. So this could be W0, this could be W1, this could be W2, etc. And we only grid it on the plane to the W value that it belongs. Then we do a Fourier transform of all these planes, so that you get a lot of images which are not corrected for a W term. But now the W term is just a multiplication, because we have this term here, so we can just correct for it by a multiplication instead of doing all the convolutions. We only have to add everything together in the end, and then we have the exact same image. So mathematically, it's exactly the same, but it has cons and pros. The pros is that you have to do a lot less effort with every visibility, but the cons is that you have to store all these planes in memories, and you have to do more Fourier transforms. But it turns out that if your W values are large, this is well worth it. So it's always a trade-off. It turns out that for our instruments, most of the time, this is a much better method. Now, this was the algorithm from 2014, and it has been improved quite a lot since then. Here are a few images that were made. This is, I must say, a very old slide from 2018 or so. These were the images that were made at the time. So WScreen was used to run the Gleam survey that was performed with the Murchison wide field array. It has been applied on the LWA, has been applied on VLBI data. And this is an image that I made. It was at the time the deepest image of the MWA. I don't think it is any longer, although it's still for the MWA quite deep. Now, and I discussed now two W correction methods. There's a third method that has been developed by someone at ASTRON here, by Bas van der Tol, and that's called image domain gridding. Now, this is I must say, quite a complicated method, but I'm going to briefly try to summarize what it does. So this method, instead of, when you have a visibility, it splits the UV plane in little squares, like drawn here. And every visibility is basically only placed in that little square. But then instead of convolving it, what is actually done is that we calculate the contribution of that visibility in image space. And that's by itself quite expensive, because even in a little square, this is going to be a little image. And we can correct for the fact that it's, of course, not the entire UV plane. You have to do some phase shifts, etc. But we still have to evaluate many sines and cosines that are contributing from this visibility. But the advantage is that this can run very well in parallel. You can even do this on graphics processing units, on GPUs, and it turns out that it's very, very well suited for this. Now, because we are already calculating this UV grid in image space, there's another advantage, and that is that it's also very easy to apply other image-based effects. And one of those is the ionosphere. If you want to correct for the ionosphere in imaging, you can do that reasonably cheaply with this method. Okay, now here's an example of also quite long ago. So it does not really reduce the amount of operations, but it parallelizes very well. And moreover, because we are already in image space, we can do image-based corrections like the W term, but also the ionosphere or the beam. We can correct that for free. And it also results in very high gridding accuracy, which I will talk a little bit about. Okay. Now, and just to remind you, what we need to do in imaging is actually correct for a very complicated beam if you're talking about LOFAR, because every station has a different beam. They are rotated in different ways, which was done to reduce the effect of if you have only one beam, you get systematic. errors, and by rotating it, you sort of average out all those systematics, and I think that indeed worked very well. But what we need to do for every visibility basically is correct for the right beam, and this is also a time-dependent thing. So if you would see this image over time of those beams, they would slowly become more elliptic and rotate a little bit, etc. Now, then this was further development of the W stacking method, I would say. There's someone called Martin Reinecke who implemented an even better W stacking algorithm, which also corrects in the third dimension. Basically, what it does not only place a visibility on one plane, as in the W stacking method, but it places this on several planes with a convolution function. And by doing so, you can get a much higher accuracy. And moreover, because he more or less started from the beginning with this idea in mind, he also made a lot of optimizations to make things faster. So this is sort of, sometimes you get your lunch not for free, but this is sort of a free lunch because it's both faster and it's more accurate. Yeah, and since about a year, it's also the default gridding algorithm in WScreen. So if any of you runs WScreen, this is the algorithm that's used by default. Now, when we talk about gridders, I think it's also good to mention accuracy a little bit, and what that's important is, for example, for this project that I'm in, the epoch of ionization, I'm not going too much into science. I'll keep it technical, although this is also where my heart is, but can't cover everything. But in epoch of ionization projects with interferometers, what we try to do is we measure a power spectrum, and a power spectrum looks like this. It's a two-dimensional power spectrum that we mostly used, and on the horizontal axis is basically the scale on the sky, such that large scales are on the left and small scales are on the right. Basically, it's the Fourier transform of your image, so you can see it as the UV plane, but then averaged in circles. And the vertical axis is the frequency direction, but then also Fourier transforms in such a way that things which don't fluctuate in frequency are in the bottom left, or in the bottom, I would say, and things that do fluctuate fast are higher up. And this allows us to separate sources from what we think the EOR would look like, because sources, they have a certain response, they are smooth, and because of the instrumental effects, we sort of get a wedge here where all our sources are located, and what we think we could see here then is the contribution of the epoch of ionization, because the epoch of ionization is not smooth over frequency, so they would be go higher up in this power spectrum. Now, why I'm telling all this is because we try to do this with gridding, but we need a very high accuracy to be able to make this separation. Because if we introduce little fluctuations in frequency, then sources would go up in this diagram, and that is not what we want, because then they sort of hide the EOR signal that we would like to observe. I'm going a bit quick over this, but basically already a few years ago, I did some simulations with gridders, and I simulated a sky model with a realistic number of sources, and I made this power spectrum after gridding. Now, and if you do the best you can, that would be a direct Fourier transform. So basically, for every visibility, you would calculate exactly what the image contribution is. This is super expensive. I remember that I needed a full cluster for a week or something like that to do this. But this looks like we would like to see. There's this line where all the sources, the power of the sources is below, and where the EOR could be, there's emptiness as we want. You can forget about this horizontal line. That's it's because of the polyphase filter, but I'm not going to go into that. That does not have to do with imaging. Now, if you do nearest neighbor gridding, so you take a visibility, you just place it only in the cell that is closest to, you get something horrible, and that looks like this, and you would not be able to see the EOR here. Now, with a very old WScreen version, this is what you get. It's better, but it's still by far not good enough for such a experiment. But you can tweak the parameters and then you get something like this, where, well, at least we have some free area, and this is at a very low level. So remember that this is logarithmic, so even these colors are not that hard, of not bright. And if we use image domain gridding, we get also something which looks perfect. And with this new gridder, I don't have a result for that, but the new W gridder, it also looks like this. So things have improved quite a lot over the years. Now, these are the responses. I'll go over this. This is not so interesting. Those are the responses per different parameters that you can choose. So that's about grading. I haven't heard any questions so far, so I just continue. But if you have any questions, just raise them. So deconvolution. I'll have a quick look at the time. Oh, I'm already taking quite some time. So one of the new things in WSClean is a fast multiscale clean method. There is a method in CASA to do this, but it's again quite slow. And in particular, if you wanted to use this together with multi-frequency deconvolution, it is very slow. So I wrote a new method which takes some assumptions and some shortcuts, and it produces very good results. These are the timings at the time, and I must say it has become about 10 times faster since then. So maybe CASA also became faster. I don't know that, but some while ago this was a comparison in speed. So if you use a single frequency, it was already over a order of magnitude faster. But if you use multi-frequency, it was like 3 orders of magnitude faster, and this has only become more. So that is very nice for big images, of course. Now, another method that I implemented in cleaning is automatic masking. And what that means is that you clean up to some thresholds. So you remove all the sources up to some threshold, say 5 sigma. And then you remember where you've deconvolved sources. And after that, reaching that threshold, you continue, but you only allow deconvolution at the, oh, I hear some noise. You only allow deconvolution at the positions that you've already found before. And particularly with multiscale, you will only allow Gaussians of the same size at the same position. And this is very effective, because if you use a mask and at something which is large, a normal mask, then the clean would be allowed to place many small components in there, and that gives you a lot of freedom. So that's what you not want. But that's solved with automatic masking. So here are some results already a long time ago. But this is on a point source field. And if you look at the residual that you would get with a normal clean, already very deep, 2 sigma, that's normally not what you want, because then you are already deconvolving the noise. But the automask residual looks like there's almost no sources left. If you're very careful, you see some artifacts on where sources would be, but this looks very good. There was also for multiscale of sources that are a little bit resolved like this. So the residual shows basically nothing left. And here's another resolved source that also works very well. So this is what you would get with traditional multiscale clean, and this is what you get as a residual. This is not normally what we look at, of course. We look more at elements like this. But you do want the residual as clean as possible, such that your flux values are as accurate as possible. Okay, now there's another method, I call this now subimage clean, where you can split your image into little parts, and all those little parts are deconvolved independently, and then they are stitched back together before the gridding cycle. And this works very well to speed up things. You can also push it to different cores on your processor, and things are smaller, so they become faster because of this. Now, there's another method called forced spectrum clean. If you're interested in making image cubes that also have a frequency axis, this can be interesting. Basically, what this method does, it gives you a prior on what you think that the spectral indices are. And this sounds a little bit like chicken-egg problem that, well, if you first need a spectral index map to make your final image map, what do you gain by that? Well, the gain is that you can make a rough estimate of it, and you can do smoothing, and you can also use different instruments to sort of get an accurate map of that, and then use it as a prior, so that you're really tweaking it for what you want. And this works very well. This is the source 3C196 from the paper by a PhD of mine, Emilio Cicotti. And he shows that the residuals are better, but what's most important is that the model looks now also much more physical, because if you look at the normal model with multi-frequency clean, these components have a basically unphysically high and different spectral indices. They can easily go up to sort of like -10 or so, and that doesn't happen with this method. So if you go into calibration afterwards, something like this is much nicer to have. Okay, this is another result. We're going a little bit faster over that now. Now, another method that is in WSClean is to deconvolve with different point spread functions, because they can change spatially. You can have a different point spread function for an image in the top left, for a source in the top left of your image than in the center. And one of the reasons for that is that in LOFAR we have larger stations at the international stations, so there are more tiles in there, and that means that the beam is smaller. And because of that, if you move further away from the center of your image, those long baselines no longer contribute. So your sources basically become larger in your apparent image of the sky because of this. Now, Stefan Weinholz wrote a paper about this, and this is now also in WSClean, and it works very well to reduce the artifacts. Oh, here's a very dramatic image. It's not always like this, but it was nice to demonstrate. So in this image, if you don't take care of the changing point spread function, clean basically completely diverges. But if you do use this method, it works much better. Now, and nowadays there are also 100K by 100K results, only really like a couple actually. So Fritz Zweyen and de Jong, they published some papers about this. This takes still very long, a week on a sort of big cluster, 100K computing hours for an 8-hour observation. But it does show that clean is actually very scalable, because in this image, the cleaning, so what I really mean with that is that the deconvolution cycle is not the most expensive part. It's really the gridding that's taking most of the time here. Now, we also do this with faceting, but I'm not going to talk about that. Now, there's a newer method, and I've done some tests with this. There are many papers about a technique called compressive sensing techniques, which would map very well on deconvolution. But I must say, I'm a critic of this method, basically since they are rather slow, although that's getting better. But there's also not so much benefit for astronomers to use these super fancy methods. They often don't work so well in real scenarios where you still have a little bit of calibration errors. They also try to get rid of the restoring, where we place points back on the image, but rather they just want to use only the model image, and that does not work well with many of our science cases. So this is sort of my opinion about it, of course. But nevertheless, also clean has some weaknesses. This is a very simple point source clean, and what you see is that the source looks very unphysical. This is not how. This is purpose A, by the way. The source does. It's a signal. It's a supernova remnant. It does not look like it would be in the sky, the model, but of course we almost never look at the model. We convolve this with a little Gaussian, we store this in an image, and that's what we look at. And then it looks fine for what we want to do with it. Okay. Let me see how the time is. I am sort of running a little bit out of it. Now, I'm going a little bit over AO Flagger. So AO Flagger is a RFI detection method. This was basically the first thing that I did when I went into astronomy during my PhD. Yeah, and I can quickly go over how it works. It works on the amplitudes of such a time frequency image, as I showed you in the previous slide. It starts by removing the channels and times that look very bad just by basically looking at the RMS. Then it estimates what the sky signal is, so sort of below the RFI or around the RFI, so that you get an image of that, and then you can subtract it, and what you're left with, you hope, is only the RFI. And does this basically using a high-pass filter. So it's left with all the rapidly fluctuating signals. Then in thresholds, and this is a special thresholding operation where it looks for lines in this time frequency space, because yeah, RFI often looks like a line. It's either constant in frequency and on for a longer time, or it can be a bit of burst, and then it's basically a line in the frequency direction. It's a short time, but covers many channels. Now, and then there are some more operations. I can show some examples of this. So this is what goes in. This is such a time frequency image. This is of the Westerbork synthesis radio telescope. Very dramatic. It's not so good at low frequencies. So all the yellow lines here is radio frequency interference. So we would like to flag that. So first step, remove the very bad channels, then estimate a first contribution of basically the sky signals. And you see, for example, there is still a little bit of contribution of RFI here. Also here, all these lines are still some contribution. But nevertheless, it's a rough estimate at first, and that works to get a better estimate. So now we're here. We have removed our first estimate of the sky. Then we do this thresholding operation, but we'll iterate that several times so that we slowly build a better estimate of a sky signal, and then we're left with this. Then we combine all the polarizations. We have 4 polarizations in this case, and then in the last operation, we basically extend all the lines that we see a little bit, like this. And this helps to sort of, because many of these signals, they slowly pop up and slowly fade away, and there's some delay in when you detect them. So by using this extension, which is called a skill invariant rank operator, you still flag them at an earlier time. Very quickly, one of the things I've worked on, so initially the strategy with AO Flagger was in an XML file that was very convoluted and not well documented. In AO Flagger 3, I changed this so that this is now actually a script, and I first tried to do this with Python, but Python did not work well for this, because you need to push so much data through it that there was a lot of overhead. I can give a little quick demonstration. I hope you can still see my screen. So I'll just open the same Westerbork set here in the RFI GUI. This is part of the AO Flagger software. So I'll open it. It asks me, well, which baseline do you want to open? Load it. And then it shows this, and all the black here is already flagged, which is not very good. So let's remove it. This is a single baseline, the data, and there's this play button which runs the default flagger. Now this is, I would say, much overflagged. This is too much from what I want. So now you can go to this Lua script. This is the whole script that runs here. And there are many parameters here which you can change. And in this case, what you probably only want to change is the base threshold level. It was at 1. So if I change it to 1.5, and I can run it again, then you see that it's much cleaner. It doesn't flag so much of things which are not really RFI. It's always hard to estimate where the separation is. So yeah, that works well. You can also do much extremer. If you say, well, I only want the strongest RFI, you can do this, and I put it to 5 instead of 1.5. Then you see there's some residual RFI. Okay. Don't save. I'll go back. Yeah, if you want to use this, there's a lot of documentation online about it. You can always mail me, also for WScreen, by the way, if you want to use it and you can't get it to work or something like that, or you need to tweak the parameters. So in the last sort of 3 minutes, I'll go over a compression technique that I developed. It's called DISCO, which stands for Dynamic Statistical Compression. And basically what it does, it compresses your data with a factor of 4. And it does this in 2 steps. It normalizes the visibility such that they're all at the same level. And this is important because particularly different antennas can have different scalings because they have a different gain. They can be larger, smaller, in particular VLBI, you have different dishes. Also, you have a passband. So at the edges of the passband, you have less sensitivity. So the first step, normalize that so that it's all, say, between 0 and 1 or -1. And then in the next step, we use a nonlinear quantization and some form of bit packing. Now, normalization I explained. The quantization basically means rounding into a nearby value. But the special thing in DISCO is that it does not have a uniform grid where it rounds to, but it uses a grid that's more dense near 0. Because we know that with Gaussian values, there are more values near 0, so we can sort of make an optimal compression where things near 0 are more accurately compressed. Now, and if you do that, this is, for example, the compression of a single curve. And another trick that you use is that you use something called dithering, that sometimes you go up and sometimes you go down if you need to make the choice. And if you do this in a statistical unbiased way, if you do this many times, if you average basically visibilities together onto a grid for the image, you slowly build a much more accurate representation of this curve. Okay. Now and yeah, if you do this, you lose a little bit of sensitivity, but it's normally only like 0.1% of your system noise. So you already have noise in this image here, and the noise that you add with this method is basically insignificant. Now for LOFAR, having basically 400 petabyte or 100 petabyte to store for our archive, that saves us basically probably several hundred Ks per year or so. I don't know the prices so much, but it's expensive to store it. Now, and then I'll skip this. I can just say that, yeah, there's a the challenge of writing such software is that you need many of these aspects together, and you need high performance. The software is very complex. The algorithms are very complex. You often need experimentation. So in the beginning, you don't want to spend too much time making things easy to work with or documented, etc. But if you want people to use it, well, you do need it. So there's all these conflicting requirements, which I think makes it very challenging. But of course, yeah, when people actually start using your software, it's very rewarding. So I'll end there. If you want to use any of these tools that I described, these are the documentation pages, and you can also find how to download things there. I have not talked about DPCube, but that's the LOFAR calibration package. It can do direction-dependent calibration in very advanced ways, including, for example, a fit for a tech curve during calibration, also for smoothness over frequency, and with direction dependent intervals where the intervals for some direction are faster than for others. So yeah, that's the end of it. So thanks a lot for your attention.
Thank you, André, for this very nice overview of all the advanced methods. Questions? I have one question while we wait for the rest of them to come back. So the multi-scale in WSClean, what makes it, what is the key change which makes it faster than the CASA multi-scale?
There are the 3 things that make it faster. The first one is that it separates in sub-images, where I showed an example, a very simple example. Because of that, your point per function also is more local, and that provides much more efficient computation. That's the easiest one, basically, sub-image deconvolution. The other one is that in WScreen, when you need to find a peak at some point, and while doing that, that's very expensive because there you need to do all these convolutions with all the scales. Now, the shortcut that WScreen takes is that if it finds a peak at a certain scale, it assumes that that scale is going to be significant in multiple parts of the image. So instead of doing this for every peak, for a while, it only looks at that scale. And that saves a lot of convolutions with the scale function that you're using. So that saves a lot. And then if you do this shortcut, what you can then also do is only cover pixels that are high to begin with in the image. You can basically reduce it to like 100 pixels instead of the full image that you have. And with those 100 pixels, look where you need to deconvolve. So yeah, look at the peak of those 100 pixels, and when you find one of those pixels to be the dominating one, correct only those 100 pixels for the next iteration. And you can do that for a while until, let's say, a few thousand iterations, and then you need to look back at what the other scales might do. So what you can do then is, and that's almost like the Clark clean method, then you convolve again your current model with the point spread function, and you subtract that from your first dirty image, so that you restore all your changes so far in your residual image. So I hope that satisfies you in that you understand what I in the method a little bit.
Yeah, thank you. Yeah, anyone else has a question? Okay, I see Arpan has put up a hand. Please unmute and ask.
Hi. Can you please explain this image domain gridding?
Yep. Just how it works?
Yeah.
Right. Maybe it's handy to have the slide with it again. And let me see if I can quickly go to that again. Oh, it's, here. Yeah, so in image-based gridding, image domain gridding, you go over the visibilities, and if you have a visibility, basically you sort of order them a little bit on where they are in the UV plane, such that visibilities that are in the UV plane close together are also gridded one after each other. So there's a little bit of ordering of the visibilities. And then if you have such a set of visibilities, you divide them in these little squares. Within such a square, you can see it as, okay, what we could do now as well is just convolve them with the convolution that we need for W terms, and there's also a grading correction convolution that needs to be done. And then we would be done. However, in image domain gridding, we take a different approach now. Within this square, we basically look how the contribution in image domain would be. And the contribution of these visibilities in image domain, they are still limited to within this square, because, I mean, we know that if we convolve them, they would be within this square. So if we take the Fourier transform of this little square, we get actually an image that is in angular size as large as the full image. However, it's at a much, it's shifted and at a lower resolution, basically. That's sort of how you can see it. It's not quite image space, something similar to image space. Now, and there we can, the contribution of a visibility is a sinusoid. So we can just calculate, you can think this as doing a discrete Fourier transform at this point, a direct Fourier transform, but only within the square in image space. And then to go back to UV plane, we take a Fourier transform, and then we have the full contribution of this little square of visibilities. That's in short what it is. And there need to be a few corrections, like when you place this back on the UV plane, you need to shift the faces a little bit to correct for the fact that this is a rectangle which is not well, it's at a specific place in the image.
Okay.
Does this help a little bit?
Yeah, I understand the whole thing. And so the observations which are longer in the like an 8-hour or 16-hour observation, they will get much more advantage in this method because most of the points are filled rather than a very snapshot coverage of things, doing a regular gridding. Or the regular gridding will have a more advantage compared to this when you have a sparse UV coverage or your antennas are placed in a very sparse, like for VLBI case kind of stuff.
Yeah, if you dense coverage will provide indeed the most of this method. Indeed, exactly as you say, because they will be, you won't have so much little squares. If you have one very long baseline with only one frequency, then that's sort of the worst situation for this, because then there are only few visibilities together in UV plane. So yeah, you're right. The more visibilities you have in general, the more that you benefit from IDG. But there are a lot of trade-offs that, because if you have a very wide field of view, you also, these rectangles also become larger. So it's having a fair comparison is very hard. So you could say that IDG is in some cases quite strong, but there are definitely also cases where you would rather use a regular convolution function. Yes,
okay.
and in fact, this gridder is used less often with LOFAR. For many reasons. I think I can talk half an hour about it, but maybe let's not do that right now.
Yeah, okay. Last question, just how do you choose the size of the squares? What decides the size of the squares? How to properly sample the UV grid?
I think it's sort of a hard-coded value based on empirical experiments.
Okay.
But you can set it on the command line how large it is, and it's normally something like, I think, 64 by 64 pixels, such a square.
Okay.
On that order, but it depends on how large your image is going to be, because if you have a large image, you have large W terms, and those W terms, they have a convolution kernel which is larger, so then the rectangles also need to be larger. So yeah, there are many dependencies on that.
Okay, thanks.
Yeah, next question. Please go ahead. Janvi, please go ahead.
Hello.
Hello.
Am I audible? Yeah.
Yes.
So I had a question about automatic masking. Is there any advantage to the automatic masking that is there in WScreen over the one that's there in CASA?
Yes. And one of them, the advantage, well, I think the automatic masking in CASA is based on sort of, I must say, I'm not entirely sure what CASA does, but as far as I know, they don't do the same thing as WScreen, in that if you find a Gaussian, you only allow the Gaussian with that size to be placed there. And that has a huge advantage, because if you put the whole Gaussian in your mask, so basically say an ellipse around where you found the Gaussian, then in the next iteration, you're allowed to put little point sources there. And that, by basically, as soon as you have that situation, if you have a diffuse source, you have placed one Gaussian there, then the deconvolution is going to place many point sources on the residual to absorb the noise that's also there. Basically the small scale noise values that are there. So that's an advantage of doing this with WScreen. There's another advantage of this method. Well, that's maybe not so much multi-scale or automask related, but you also get a source list out with WScreen. And as far as I know, that is not how it works in CASA. If you do multi-scale, you can get a source list out, but it's not based out of Gaussians. I hope I say all this all right. I'm not an expert in CASA, so.
Okay, thank you.
Yeah, any more questions? Please unmute and ask. We can maybe take another couple of minutes.
Yeah, sure. I hope it was on the level that you could understand it, and while it was also not too repetitive, it was hard for me to estimate. But
No,
but
it was fine, I think. Vishwesh, do you have a question?
Yeah, I probably missed it during the talk, but I just want to know what sort of computing resources does it take to image a typical, low-FAR observation, say from rise to set of a particular field? In terms of, do you use a cluster, and how long does it take for the whole thing to go through and get all your data products?
Right. Well, most of our processing is still on a single node, so we use a single computing node. And for what you described, basically the full bandwidth, 8 hour indeed, from rise to set observation takes several days, let's say a week or so, with the Raptor pipeline. The survey pipeline is faster. I think that one takes about 3 days, I think. So it's on that level. But so far we've always used single nodes, and if we need to process more, we basically process a different observation on a different node. That's our way of parallelizing. That's not what we envision, what we want to do for SKA. There we really want to have one observation and be able to process it on, say, 20 nodes and divide those 7 days into, say, half a day per observation by doing so. And those nodes are quite heavy nodes. We normally use something like at least 128 gigs or 256 gigabytes of memory. And then, the faster the CPU, the better, of course. So we can make very efficient use of multi-core machines. So many of the people that process low-FAR data have like 100-core machine where they can do very efficient calculations. Yeah, most of the calculations is in this gridding step, and also the calibration, which I didn't talk about, but the direction-dependent calibration is also still a very expensive step.
Thank you very much.
You're welcome.
Suman, please go ahead. Suman?
Thanks, Andre. So I have 2 questions. So one is a bit technical. So in AO flagger, if the sky changes, like let me say I'm doing a drift scan observation and the sky changes with time, so can it flag actual sources because they can get into the field and move away?
Well, in short, yes, it could, but not in the scenario that you describe, I think, because those changes are always very slow over time. It's not that you see a source and if it's not a transient source, it would not suddenly be out of the beam. That takes, say, a minute or so to go from full to nothing, if it goes through a deep null or through a side lobe or something like that, at least. And it's not sensitive for those kind of changes because they are still smooth changes, so they sort of, the high pass filter filters those changes out. What you do have to be very careful is if you have, for example, if you have an H1 observation. I've seen observations where you can just see by eye the H1 lines in your time frequency plot, and if you see them by eyes, they're certainly going to be flagged by a flagger because it is sensitive. It looks for those kind of lines. There's several ways for how to handle this, and I wrote also a few years ago a paper on how to deal with this with Aperitif, the Westerbork upgrade. And basically we more or less ignore the band where we expect the H1. That's sort of our best method, and we can get away with it because it's a protected band, the H1 band, and it's only for some observations that you if a galaxy is visible in H1, at least for Aperitif, it must be a close by galaxy, so it has not a redshift that makes it appear at much lower frequency. So yeah, that's sort of what we do. The only thing that we still do is look for bursts in time, and we do flag them throughout the H1 band as well.
Okay. So so in MWA, it's like the data is stored in a like 2-minute snapshot kind of strategy, right? And now if you so let me say within this 2-minute sources,
is in the field of like very close to the first null or something. So what happens then?
So if you have a source very close to the null, well,
Yeah.
it is going to be faint then. Well, unless it's Kase or something like that. But even Kase is going to appear, it's going to disappear sort of slowly. It's not like you have a huge dip in its sensitivity. So if it goes like this, so in a smooth way, the high-pass filter basically filters the signal of that source out. And it's normally not an issue, as far as I've seen.
Okay.
There are probably examples where you can do something extreme, where you do flag this a little bit, but I have not seen this much of an issue.
Okay. And I have a small question about something what you have discussed in WScreen, which is direction dependent point spread function. So so you showed a dramatic improvement in the deconvolution artifacts. How is this being like? Why there is this dramatic improvement? Can you just repeat again? Sorry.
Yeah, sure. I'll not try to find the image now because it probably takes me a minute. But it mostly comes from I described that LOFAR's high resolution baselines, the long baselines, they have a smaller field of view. So that means that if you have sources that are sort of outside that field of view, they could still be visible at the short baselines, but not the long baselines. Now, what you then get is that sources in the center are very sharp because they are seen by all the baselines, but sources further away have larger point spread functions. Now, if you don't use direction-dependent point spread functions, you would basically calculate your point spread function in the center, which is very sharp, and then you try to deconvolve those larger blobs at the edges with that. And that can lead to divergence in the algorithm. Basically, the assumption that your point spread function is correct is no longer valid. And then you get that, you get a sort of a harmonic behavior in that it finds something, but it actually makes it worse by finding it. And then it finds an artifact of that previous removal. And slowly it builds just more negative and positive sources, and it diverges. And that was what you saw there. Does this answer your question?
Yes, thank you. Thank you very much.
Great. Good questions all along.
So, I don't see anyone unmuting themselves. So in the interest of time, I think we will wrap up. Thank you, André, very much for this really a nice overview of the latest methods. So thank you all for joining, and see you at the next RATeS seminar.
Okay, thanks a lot for inviting me. See you all at the next conference or something like that. Bye-bye.
Thank you. Bye.